This one is an example of the kind of calculation you'd have to do if you wanted to calculate the pH of an acidic salt in water. The question, what is the pH of 0.88 molar pyridinium chloride? We will look at the steps as we go through the problem. First question, is the given compound acidic or basic in water? This compound, pyridinium chloride, has the chloride attached to its name, which indicates it's got a negative ion, Cl-. That means the rest of the structure must have a plus charge. This is one of those nitrogen compounds that has an H attached to the nitrogen and has a plus charge. It is like ammonium, NH4+, and these are acidic. You should remember that type. Being that these are acidic, our next job is going to be to write the net ionic equation, and since it's an acidic compound, we need to write the reaction to form the conjugate base of the compound, and then also H3O+. So let's start here. We'll have C5H5NH. Now, are we going to put the Cl in or not? We want to write a net ionic equation. The Cl- is a spectator ion. You note that it is the conjugate base of a strong acid, and it is not included in these pH calculations because it just doesn't do anything to the pH. So we leave it out. That will make things look a lot better. As usual, we will take our acid compound, add water, create our conjugate base. Conjugate base is 1 less H. And the H comes off the nitrogen, and it's 1 less H plus, so that's 1 less plus charge as well. And we have transferred that H to the H2O, so now we have H3O plus. That would be our reaction equation. Now that we have a reaction equation to do our ice table, we're going to need an equilibrium constant to go with it. Because this is an acid, we need a Ka. So we'll need the Ka for the acidic compound. That is our ion, not the whole compound, just the ion that is acidic, C5H5NH+. We normally look up the K values in tables, but when you have an ion, the values are normally not listed in the tables. What you will have to do instead is use the relationship that I've listed here, which is Kw equals Ka times Kb of the conjugate base, and in order to calculate the Ka from the Kb. So you will look up the Kb of the conjugate base, not this compound, but the conjugate base, which would have to be 1 less H plus. That compound is known as pyridine, but I think you will find the formula in the table, so you won't have to worry about the name. When you look that up, the Kb is 1.7 times 10 to the minus 9th. If the Kb is 1.7 times 10 to the minus 9th, you can calculate the Ka. The Ka comes out to be, I'll keep an extra significant figure here, 5.88 times 10 to the minus 6th. This is actually a 2 sig fig number, but I'll just keep an extra one for now. Okay, let's set up our ice table. Those are always fun, right? Our initial value for the pyridinium ion is going to be 0.88. Remember that if nothing is mentioned about the products, those are 0, and water is not included in our K expression. We have plus X on each of the products. minus X on the reactant. And there are our equilibrium values. We will put those equilibrium values into the equilibrium constant expression and solve for what we need. Putting our equilibrium values from the ice table into the equilibrium constant expression gives us what's shown here. 5.88 times 10 to the minus 6 was the Ka that we determined previously. We can assume, to try to simplify the math again as usual, that the x that's subtracted from the 0.88 is small. We'll have to check our assumption, but we will start out by saying it is just 0.88. When you solve that, x comes out to be 2.27 times 10 to the minus 3. Since 10 to the minus 3 would be one decimal place past the 0.88, you can see that without even doing a calculation, that number in fact will be negligible, so our assumption is okay. We therefore have solved for x. We need to look back at our ice table to see what x stands for, and in this case, x stands for H3O plus concentration at equilibrium, because this was an acidic compound and formed H3O plus. That makes it easy because then our pH is just the negative log of our answer here. That comes out to 2.64, which is 2 decimal places because there were 2 significant figures. As usual, you can use this method to solve for something other than pH if needed.